Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. In the last couple of lectures, I went through nomenclature and also how to prepare, aldehyde and ketone functional groups. And now that we know like how to prepare them or like how to name them, let's start getting ready for some of the chemical reactions that we can actually run with aldehyde or ketone functional groups. And remember that regardless of which molecule you picked, in both cases, aldehyde and ketone, you have a double bond between carbon and oxygen. And electronegativity, it says oxygen is more electronegative than carbon. What does it mean? It means carbon is going to lose it to oxygen, so that's going to leave carbon with a positive charge, while oxygen will gain extra electron density, so it will have extra negative charge. Now, pi bond always is going to be weaker than sigma bond, so I'm going to say sigma is stronger than a pi bond, and if there is a chance to turn sigma to pi bond, then the reaction is going to move in that direction. Okay, now, as I said, I want to go after chemical reaction of carbonyl groups. I need to know what are the factors that they are effective on, let's say, rate of the reaction or ratio of the product, different product that I might get. Do I have electronic or steric, effects? And I need to study those. But for now, let's just simply zoom on the carbonyl group. The carbonyl group, it has a trigonal planar geometry. What's the reason behind it? Because carbon, it has sp2 hybridization. Now, when I add the nucleophile to it, the nucleophile is going to go after carbon, that is short of electron. And when I add it to it, the carbon and the nucleophile, it can be added from the top or bottom. And the second you add the nucleophile, now you will get a center that it has 4 substituent attached to it. And that means there is a possibility of having chiral center. And yes, in this case, because the two R's are identical, it will not be, chiral center. But if I replace, let's call this one R1 and call that one R2, now I have 2 different substituents. And like I have, 4 different substituents, I say I do have a chiral center. That means I will get enantiomers. That's one. Now, if there is another chiral center, or let's say a double bond maybe, and there is a possibility of getting enantiomer and diastereomer. When do I get diastereomer? Whenever you have another chiral center somewhere on the molecule, not the carbon I highlighted. Okay. Now, let's study those effects. One is going to be the steric, and the second, it will be the electronic effect. The steric effect, remember, when it comes to ketones, ketone, it has two carbonyl groups, two alkyl groups attached to it. If they are bulky, then they will make it harder for the nucleophile to reach the carbon with a positive charge. I'm talking about that carbon. And, well, when we compare it with aldehyde, we have same R, let's say, but the second one, we replace it by hydrogen. Hydrogen is smaller than any alkyl group, so I'm going to say, and the carbon of carbonyl in aldehyde is more accessible and toward the nucleophile in aldehyde functional group, okay, compared to the ketone. Now, how about the electronic effect? The electronic effect, we know alkyl groups are more like alkyl groups are electron donating, and they donate more electron density than hydrogen. So, for example, CH3 can donate more electron density than hydrogen. So I'm going to say, when it comes to ketone, it gets help from both R's. While when it comes to aldehyde, I have only one R, so hydrogen cannot donate much electron density. What does it mean? The partial positive charge that we have for ketone, it will be smaller than the partial positive charge of the aldehyde. It means nucleophile will find this carbon and shorter in electron density than the carbon of ketones. And so the reaction here, it will be faster. Now, in order, to run a chemical reaction with carbonyl groups, I can use like a strong nucleophile, or maybe I can, run the reaction with weak nucleophile. But in order to use weak nucleophile, I need to kind of like prepare the starting compound. What do I mean by prepare? Make it more reactive toward, like electrophilic or nucleophilic, reactions. And we can play with that one by changing the acidity or basicity of the solution. Okay, and let's study some example. In this case, I have a carbonyl group that attached to 2 methyls. Second molecule, again, is the same one, but this time I replace oxygen by NH. And then I have methyl attached to the carbon. The third molecule, again, we have oxygen, but oxygen attached to hydrogen. We have CH3, CH3. Okay, let's study the steric effect or the electronic effect of the substituent that attached to the carbon. Okay, that's the carbon that I'm studying. Okay, I have an identical substituent attached to the carbonyl group. Okay, or the carbon, not the carbonyl. I need to be careful about this one because one of them is the NH. And okay, so methyl is going to be the same. So the difference is not going to come from the methyls. Next one is like I have this. electronegativity is telling me oxygen is the most electronegative. Then we have nitrogen. Okay, and how about the lone pairs, or the formal charges on the oxygen and nitrogen atom? First one, we have oxygen with 2 lone pairs, and the charge on it is going to be 0. How do I know 0? Okay, here I'm going to remind you how to get the formal charge. Just simply draw a circle around the element and say this. What's the group for it? Is group 6. How many electrons inside the circle I see? I see 6 electrons, so it will be 0. For oxygen, for nitrogen, it's not octet. It has 6 electrons around it. I'm going to add 1 lone pair to it, and it will be octet in that case. Formal charge is 0. And for oxygen, and we need only 1 lone pair around it, and it will be octet. But let's check the formal charge for it. Oxygen is a group 6, but I see only 5 electrons around it. So oxygen, it has a +1 charge. Now, let's call this one number 1, that's number 2, and this one number 3. Okay, I want to see which one of this is more reactive, like toward, like a nucleophile, reacting with a nucleophile group. And the one that it has oxygen attached to carbon, it will be more reactive. So the choice is going to be, the first choice is going to be in between number 1 and number 3. But number 3, it has not only it has oxygen, also it has a positive charge on oxygen, which is not cool to have a positive charge on oxygen. So I'm going to say the most reactive compound, it will be number 3, because it has oxygen with a positive charge. And then number 1, and next one, it will be number 2. Why? Because it replaces oxygen by nitrogen, which is less electronegative. So I'm going to say, yes, nitrogen is going to pull electron density from carbon, but not as much as, oxygen. So if you, label those as, say, F1 here, F1, F2, F3, I'm going to say F3 is going to be the strongest one, then F2, and then F1. My bad. F3, and then this one, F1, and then F2. Sorry about it. Okay, another example. We have carbonyl groups, but this time we are talking about different functional groups. When I say different, it can be aldehyde or ketone. Well, the first example, forgive me, like in first example, I kept the substituent identical. I did not change them. The only thing I changed the atom that attached to oxygen. In this case, we keep oxygen as it is. Okay, we don't change that part. Only thing we are going to change the substituent that's attached to the carbonyl. Okay, let's go with this. Here we have CH2, and then a bromide. This one, CH3, CH3, CH3. This one, CH3. Here I have hydrogen. This one, CH2. Now I put bromide here, and I have hydrogen there. Okay, let me change the color for this one. Let's say this one to be bromide. Okay. Bromine atom, well, in this case, a bromide is an electron with a joint group. So it's going to pull electron density to itself. And that means it's going to have it's going to leave positive charge on carbon. Now, we know CH3 is electron donating group, okay? And is more capable of donating electron density than hydrogen atom. Well, Br is an electron withdrawing group. Okay, so let's say this is 1, that's 2, 3, and we go 4 here. And let's compare this molecule. Okay, I'm going to say the one that has less electron donating group, it will be the most reactive compound. Okay, or the one with higher, the highest partial positive charge on carbon. And in this case, it's going to be an aldehyde molecule. So I need to pick one of this aldehyde. Okay, I have 2 aldehydes, 3 and 4, and because the bromide is attached to CH2 number 4, and the bromide is going to pull more electron density and like from the system. So number 4, it will be the most reactive compound. And then we will have number 3. And after that one, okay, now let's compare 1 and 2. Okay, 1 and 2, both of them are ketones. These 2 are ketone. The one that has less electron with electron donating group, it will be more reactive. And between 1 and 2, yes, in both cases we have carbon attached. I'm talking about this carbon. We have carbon atoms are attached to the carbonyl, but this, okay, forgive me, this carbon is CH2 that is attached to electron withdrawing group. So that's going to donate less electron density to the carbonyl. So I'm going to say next one, it will be number 1, and after that one, it will be number 2. Number 2, it will be the least, reactive technically compound. Okay. Another example. Okay. What do we have here? In this case, okay, as you see, when, like we have oxygen attached to a carbon through a double bond, and in one case, like we replace the substituent, for example, the hydrogen, we replace it by a methyl, and then methyl, we replace it by a CF3. Also, last example, last molecule, we have a positive charge on oxygen. Okay, I'm gonna start with this. I will add lone pair to oxygen to make it octet, and except the last molecule, all these molecules have 0 formal charge on oxygen, while the last one, it has a +1 charge. Okay, so the most reactive component, it will be number 1, last molecule. Okay, let's call this one 5. So I'm going to say the most reactive one, it will be number 5. Okay, because we have a positive charge on oxygen. Okay, and next thing is, keep this one in your mind that, alkyl groups are electron donating groups, and they will donate more electron density than hydrogen. Okay, well, fluorine is an electron withdrawing group. So I'm going to say the more carbon we have attached to the, technically to the carbonyl, the higher electron density we can donate to the carbonyl. So I'm going to say the tertiary butyl will donate more electron density than, for example, say an ethyl or methyl. This one more than hydrogen. Okay, and if you take the hydrogen attached to the methyl and replace them by fluorine atom or electron withdrawing group, in that case, not only carbon, it will not donate electron density to the carbonyl, it will actually pull electron density from it. So this one, it will be electron withdrawing group, while these two are electron donating groups. Okay, so again, let's review all the substituent. Okay, we have aldehyde and ketones, and so I'm going to say between these molecules, the one that's like this aldehyde, and also it has a positive charge, it will be the most reactive. Okay, number 5, it has CF3 electron withdrawing group, and also positive charge there, and it's an aldehyde. So everything is exaggerating the positive charge on carbon. So I'm going to say number 5 is really reactive. Next one is going to be number 4. Why number 4? Because number 4 still is an aldehyde. And then after that one, okay, now let's look to number 3. Okay, how about number 3? Why number 3 is less reactive than number 4? Number 3 still is an aldehyde. Okay, so maybe I should say number 3 still is an aldehyde, but why is less reactive than number 4? Because you have a methyl that it can donate electron density. Well, here we have like a CF3 that it will pull electron density from carbonyl. So this one is donating. Well, here we are pulling electron density from carbon. We are exaggerating the positive charge. And so those 3 are aldehyde. Okay. Now, anything after this one that I'm reviewing, it will be ketone. Okay. A ketone with less substituent or smaller substituent, it will, be more reactive, both steric and electronic, through a steric and electronic, window that you looked at will be more reactive. And so I'm going to say number 1, it will be more reactive than number 2 because, amount of electron density that we donate to carbonyl group, it will be less compared to the tertiary group. That's it. It has a 3-methyl and it can donate plenty electron density there, and that's going to saturate the carbon. So the positive charge is going to be smaller and smaller. That means it will be less electrophile carbon. And this is going to be the end of this lecture, and thank you very much.